Okay, so in this video we will see the second part of the virtual ground concept. So till now what we saw is like ideal cases. Now let's see the some practical case, and this will be like a actually used in the circuit. So let's see what is the concept. So if you see here closely, so what is the given things for us? So we have 2 ampere current and 1 ohm resistance available and 2 volt node voltage is here present. Similarly 2 ampere current, 1 ohm resistance, 2 volt node voltage, and this is the 6 ampere current. Okay, so from this we can do the KCL and we can find the value of the this voltage, and it will be 1 volt. Okay, so this is 1 volt. Okay, and the current through each resistance comes out to be 1 ampere. Okay, so this is 1 volt and this is 1 ampere and this is 1 ampere. Now let's go to the what will happen if we change our dynamics. So what happens, because of the input voltage in the MOS, if we increase this input voltage, we see the increase in the current, and in opposite side, if we decrease this voltage, we see the decrease in the current. So what I will do here, let's say the current increased by 1 volt and 1 ampere. Okay, if you see here, current is increased by 1 ampere and here current is decreased by 1 ampere. Okay, now since this is 6 ampere fixed current, okay, and also important thing is this node voltage is decreased by 0.5 voltage and this voltage is increased by 0.5 voltage. So important point is node voltage decrease here and increases here equally. So delta V here is 0.5, which is same in both case. Here also delta V is minus 0.5. So decreases by 0.5 and increased by 0.5. Okay, node voltage, and current is increased by 1 volt and current is decreased by 1 volt. So here I have taken the actual example that what will happen if this voltage decreases, this current decreases, this voltage node voltage will increase. So we will see all this concept in another video, but for now let's see the delta V here is 0.5 minus 0.5 and here delta V is 0.5. so current increased by 1 ampere, current decreased by 1 ampere, voltage decreased by 0.5, voltage increased by 0.5. In this case, if you calculate this node voltage from the KCL, what you will get? You will get again same 1 volt. So this 1 volt is same as this. So change in the voltage is 0. Okay, and so first point is this current increase by same amount, current decrease by same amount. Second point is voltage decrease by same amount, voltage increase by same amount. Then we will see that this delta V change is 0 voltage. And from here also you can see that the current through this resistance will be decreased by 0.5 ampere, and in this branch the current will increase by 0.5 ampere. Okay, so the decrease in this current branch, the decrease in this current branch in this resistance, the decrease in this resistance current is equal to the increase in this current. So this is the fourth point. Okay, the important point you should remember is that this current decreases by 0.5 and this current is increased by 0.5. So all this combination will result to the basically combination number 1, that current increase and decrease by 1 ampere and voltage here decrease and increase by same amount. Then this voltage is 0, change in voltage, this node voltage, and also the current decreases by same amount as current increases here. So this is the virtual ground concept. So here if you see that the change in voltage at this point is 0. So if I draw the changes, only the changes diagram, so current is changed by 1 ampere, okay, and resistance has been remained same 1 ohm. This voltage is decreased by 0.5 and this side if you see the total current will be minus 1 ampere basically change, and this is 1 ohm resistance, okay. So and this voltage is 0.5, then this voltage will be the change voltage is 0 volt. So from here finally we can simply look that change in this current is equal and opposite change in this current. Change in this voltage is equal and opposite of change in this voltage. An important point is if this current increases, this voltage decreases, and this current decreases, increases in this voltage. So current increases, current decreases, and voltage decrease, voltage increase equally, basically plus, and the current increase is 1 ampere, current decrease here is 1 ampere, voltage decrease here is 0.5, voltage increase is 0.5. So if you see in this, whenever you see such thing in your circuit, then this potential will be, the change in potential will be 0. And if we make this in term of simply changes, only changes, let's say this is delta I, this is R, so this will be minus delta I, this will be R, then and this will be plus delta V, this will be minus delta V, then this potential will be delta V is equal to Vp is equal to 0. So this is the virtual ground. Only thing you have to understand here is that this is delta I, then this is minus delta I, and this is delta V, then this is minus delta V, then only this will be virtual ground. An important point also here to note that this increase in delta I is because V input is increased by delta V in, and here V input is decreased by delta V in equally. So effect of this is delta I. So basically input is increased by delta V in, and here input is decreased by delta V in, then only this decrease in current happens. So this is the virtual ground concept. So I think from this video virtual ground concept is clear, and we can use this in our practical circuits. The only concept here is that we need to look importantly on this voltage, what is this two voltages, drain voltages, and what is the change in the current. These are the important point to be looked in the circuit. Thank you.